In this video, we're going to do some sample problems relating to the equilibrium constant and equilibrium expressions. So think of this like another introduction to equilibrium that we saw in the previous videos, just with some more details. So as you can see, we have an equation here, and as we know, this equation exists in an equilibrium. Essentially, the rate of the forward reaction will eventually be equal to the rate of the reverse reaction. And so if you want to write an equilibrium expression to illustrate this or to determine when equilibrium has been reached, you would write K is equal to, you do the concentration of your products multiplied by each other. Each product must be raised to the power of the coefficient that is in the equation. And then you would divide that by the concentration of the products multiplied by each other. And the products must be raised to the power of their coefficients in the equation that you see there. So a couple of things you need to know before we move on is that typically, even though there are units for these concentrations, and those concentration units are usually moles per liter or molar, we usually don't report the unit for K because these exponents will vary so much, and that'll lead to so many different units of K that we don't bother reporting them. So typically, we do not report the units for K, and you don't really have to demonstrate that. The other thing is that the equilibrium constant K is affected by temperature changes because the rates of the reactions are affected by temperature changes if you increase or decrease temperature. So that'll change your K value. And so we do have to report what temperature we're typically doing an experiment at when we're reporting a value for K. And the other thing to remember is that we do not report solids and liquids in equilibrium constants because the solids and liquid concentrations are, well, constant. They don't change. So they're not going to be a factor in our expression. So here there are various examples that you can try out. Since you already saw an introductory video, you can pause this video and then check your work as I complete them once you're done yours. And then you can make any corrections that you might need to make as you go through my video. So I'll start with the first one. Here, everything is aqueous, so I know I'm going to include everything in the equilibrium expression. I'm going to write K, it's an uppercase K. You can put EQ as well for K equilibrium. You don't have to. It just helps you to differentiate uppercase K from lowercase k, which is the reaction rate constant. So we're going to do the concentration of our product. That's an SCN there, 2 plus, over the concentration of our reactants multiplied by each other. And they're all raised to the power of 1 because they're coefficients of 1, assuming everything is balanced, and it is. Let's go to our next one now. So this is our next example. So we have, they're all gases here, so they will be included in our equilibrium expression. KQ is equal to the concentration of NH3. And that's squared because of the coefficient of 2 here, over the concentration of N2 times the concentration of H2 to the power of 3 because of that there. And now we will do our final example here. You'll notice that we can write K. You can put a EQ, I'm just not going to write this time, is equal to K plus times H2O over KOH times H plus. Now, if you did that, you're actually wrong. And I'm wrong too. I made a mistake here. That's okay. Let's take a look at what mistake that was. Remember that you do not include solids and liquids. So I would actually not include the water and not include the potassium hydroxide since they're liquid and solid. So those should not be in there. And a better answer would be K is equal to K plus concentration over H plus concentration. And this is our equilibrium expression. That's a big K, not a little k, KEQ. This would be wrong because we've included the liquid and the solid. Now, remember that equilibrium means that the rate of the reverse and the rate of the forward are equal. It does not necessarily mean that your reactants and products are equal in concentration. You can have several different conditions of equilibrium, and the K value can tell you those conditions. So for example, if I have a K value that's larger than 1, what that means is that my reactants concentration is going to be less than my product concentration at equilibrium. It basically means my products are favored at equilibrium. And the way to think about it is, if you have, I'm just going to write this out over here. If you have, remember, the K is the concentration of products over reactants. So it only makes sense that if the K is larger than 1, that means the products are higher than the reactants, because your K is larger than 1. It's like having 10 over 1. I'm just making those numbers up, but that's how to look at it. Okay, so you can still be at equilibrium. The rates will be equal going forward and reverse, but your products might outnumber your reactants concentration-wise. And then if you have K less than 1, well, it's the opposite. Your reactants are favored. So your reactants concentration is higher than your product concentration at equilibrium. And that would be kind of like doing K is equal to product over reactant. And it's almost like having 1 over 10. So your reactants are favored over your product. I made those numbers up, but that would be a K less than 1 instead of a K greater than 1. And the other scenario for an equilibrium is a system where your reactants and your products are equal in concentration. Okay, so just because you're at equilibrium, it does not mean that your reactants and products are at equal. It just means their concentrations are no longer changing. So the rates of the reverse and the forward are the same. So if I'm at equilibrium where reactants are smaller than products in terms of concentration, that system will stay that way. It will no longer change. And if I'm in a system where reactants are favored over products, that system will stay that way. It will no longer change at equilibrium. And then if I'm in a system where R is equal to P, the reactants and product concentrations are the same, the system will stay that way at equilibrium. That would be kind of like having products over reactants is equal to 10 over 10, for example, which is equal to 1. And so the K value can give you information about what the system looks like at equilibrium, essentially. But you do not have to have equal concentrations of products and reactants for you to be at equilibrium. So that was some more general background information about the equilibrium concept. We saw to write equilibrium expressions and did some practice problems together. We went over the idea that you do not have to have equal concentrations of products and reactants to be at equilibrium. That's not a necessity. It's more that the rates of forward and reverse are the same. And one more thing to mention is that at equilibrium, things don't stop. So when you reach equilibrium and the rate of the reverse, of the forward and the reverse are the same, it doesn't mean your reaction has stopped. In fact, it just means that your reaction rates are the same going forward and reverse. It looks like things have stopped. Essentially, when you first start a reaction, you'll see color changes, flashy stuff sometimes, and eventually it stops. You say the reaction's over when the equilibrium has been reached because there's nothing else happening. But the reactions are still happening forward and reverse, but at the same rate, so it looks like nothing is happening. So in other words, we should actually call equilibrium a dynamic equilibrium. Because deep down, there's still work happening. It just looks like nothing's happening because as soon as something happens, the reverse happens. So the example I had given before was you're on a city bus and someone gets off and then someone gets on immediately after. It looks like nothing has changed, but people still had to move and something still had to happen. So equilibria are truly dynamic. Things do not stop moving. They still react just at equal rates, so it looks like nothing is happening anymore. In the next video, we're going to do some numerical examples that employ the use of the equilibrium constant.